Hey everybody, it's Mr. N here, and this is the 1-5 notes, and today we're going to talk about measuring and constructing angles. But first, before we get into that, let's just remind ourselves what the definition of an angle is. And the definition of an angle is that it's a figure, right here is where we're looking, a figure formed by two rays. Let's use the pointer tool. By two rays that have the same endpoint. So here's ray RS, here's ray RT. They have this same common endpoint R, so this creates angle R, and we can write this as angle R like this, angle R. You could also, since I labeled it 1 on the inside, you could say that it's angle 1. You can also call it angle SRT. Either one of those is fine. The only thing you need to be careful is if you have multiple angles that share this common vertex, you cannot just say this vertex was W. You can't just say angle W, because then which angle am I talking about? Am I talking about this angle here? Am I talking about this one, this one? So W could have been any one of these, so you'd have to clarify it by putting the 3 letters, or if they were numbered on the inside. But if it's just one angle like this, either one of these is fine. All right, so back to our notes over here. Let's take a look at what we got. And it says, the two rays are called the sides. So each of these right here, I will label them as the sides of the angle. And this common endpoint will be the vertex. So we've got the vertex and sides, and we already said that it's denoted by this symbol, which is the angle symbol. Okay, we can use a protractor to measure the angles in degrees, but I want you to note and be careful here, degrees is not the only form of measure. 360 is a full circle, but this is not the only form of measure. Just like how you guys have been used to using inches and meters and other forms of measure, angles don't always have to be in degrees. We're used to using degrees. This 360 number is completely arbitrary. In fact, this 360 number was just kind of made up. They've traced it back to the ancient Babylonians, and they were using a hexadecimal system. There's many other reasons that they've come up with this number for 360. In their hexadecimal system, imagine if you have a regular hexagon. Oops, let's use the drawing tool here. And I don't think this software will let me draw a nice hexagon, so I'm going to have to hand draw it for you, which is never a good idea for me. But let's just do this. So suppose you have some regular hexagon here, and that's not that good. But if I break this up into 6 triangles, hexadecimal system, if you go around, each of these angles is 60, right? Because we said this is a regular hexagon. So each of those angles are 60, so you end up with 360 as going all the way around. That's one way to think of it. Another way is they would look up into the night sky. So suppose this was me, Mr. Nasser, up here, looking up at some star in the night sky. And I'd say, ooh, oh, star, cool, there's a star. Well, it would take, every night I look up and the star had just moved just slightly off from what I see. It shifted a little bit. And it would take about, how many days do you think for it to come back to that exact same position? It took about 360. Now we know this number is not this exact. It's 365, right? Give or take a little bit. That's why we have leap year. So that's what they noticed. So this number 360 was pretty much magical. It fit everything. And in fact, here's another thing in math. 360. A lot of numbers are divisible. A lot of numbers go into 360. And it makes calculations even easier. So this 360 number became so magical, so they decided to use it as a full circle. but there are other forms of measure. Radians is actually the preferred one from mathematicians. Mathematicians like to use radians, and it just makes sense to use radians as far as mathematicians are concerned, because if you, and I'll just give you a quick example. We're going to talk about this later in the year, but I'll just give you a quick here example. If I draw a circle, what is the circumference of a circle? Well, it's 2 pi r, because we've come up with various other ways of determining that circumference. So here's what happens. If I call this 1 unit and call that radius, any radii I put in here is going to be 1 unit. And I make this distance, and I'll explain this again later in our course. If I make this distance from here to there 1 as well, how many of these things, these distances, do you think it will take to go around? Well, guess what? It takes 2 pi of them. So it'll take 6.28 of them, right? To change it to be not exact, but to change it, approximate as a decimal. To be exact, it'll take 2 pi of them. So this value of a radian, this measure of a radian, works much, much, much better than an arbitrary number 360 that just sounded cool and fit our needs. So that's the difference there. And but for our class for right now, until we talk about radians, which is second semester, we're going to deal with 360. So then we end up with these types of angles. We have an acute angle. It's really cute. It's so cute because it's between 0 and 90. It's really small, so it's acute. A right angle, so be careful, this one is a left angle, right, because it's on the left side. Just kidding, guys, just kidding. This is still a right angle. It doesn't matter if it looks like this or if it looks like that, okay, or if it looks like that. As long as I put the right angle symbol, it's a right angle. Then we've got an obtuse angle, so that's an angle between 90 and 180, and we've got a straight angle that measures 180. Now, let's move on to a couple other things, and we've got the protractor postulate. Just like the ruler postulate, the protractor postulate tells me I can make a protractor to measure angles. And then we've got, just like we had segment addition, we've got angle addition. I can add up angles. So if I've got these two angles, and this is what it's saying, B is in the interior of angle. Here's A, I can put point O, and I can put point C right there. And B is somewhere in the interior, and I draw that angle. Well, then I can add up A to O to B plus B to O to C to get A to O to C. So I can add those two angles up. So you could say angle 1 plus angle 2 if I label them in there. And then we've got congruent angles. Congruent angles have the same measure. So we will use this congruent symbol, which you already know. And the difference between, I've kind of mentioned it a little bit, but we'll get into it a little bit more later. Difference between congruence and equality. Equality just means I'm about to put a number in. Just think of it that way. I'm about to put a number in. Whereas the congruence, it's a more general statement. It's this angle's congruent to that one. But I don't know what the measure of them are specifically. So when I put M in front of it, I'm going to say equals, because think of it as I'm about to put a number in. I know what they are. I can measure them. So then I'll use equal instead. Adjacent angles, two angles in the same plane that have a common vertex but no common interior points. So in other words, if I draw this angle right there, and suppose I have another one here, these two, angles 1 and angle 2, are adjacent angles because they share this common, I'll put it in another color, they share this common vertex right here and a common side. So they have a common vertex and a common side. All right, let's move on to the next page here, and let's expand this out. Okay, over here we have the bisector of an angle. Okay, so a bisector, whatever angle I make, a bisector will just cut this angle in half. so that angle 1 and angle 2 will have the same measure. They will be congruent. So a ray that divides the angle into two adjacent angles that are congruent as well. So that's pretty much a summary of these notes. We are going to do these in class, but right now let me do some of these other examples for you. On this first one, it says, given that the measure of angle AOD is 4y minus 8, and the measure of angle DOC is y minus 11, and the measure of angle COB is y plus 13, we have to find the measure of angle A to O to D. We have to find all that. Well, how can I do that? Well, I know that a straight angle, we said, adds up to be 180. So if I add these three angles, the 4y minus the 8, plus the y minus the 11, plus the y plus 13, I should get a total of 180, because 180 is my straight angle, like that. All that adds up to be 180. All right, so let's work this out. 4y plus another y gives me 6y. And then negative 8 plus negative 11 is negative 19. And negative 19 plus 13 will give me negative 6 equals 180. So now I can bring the 6 over, so 6y equals 186. Let's finish solving that up there by dividing each side by 6. So 186 over 6 comes out to be 31, which is what y is. And now since I need to find AOD, I plug it back into here. So 4 times my 31 minus the 8 ends up being 124 minus 8, which is 116 degrees. Okay. Angle 1 and angle 2 are adjacent. Name their common vertex and common side. And it doesn't say it, but we are referring to this figure right here. Angle 1 and angle 2 are adjacent. Or, I'm sorry, 2 and 3. 2 and 3 are adjacent. So we have to name their common vertex. And in this case, it will be Z. And their common side for angle 2 and angle 3 will be AZ. All right, angle 1, right here, is adjacent and acute to angle what? Okay, adjacent and acute, meaning they're talking about angle 2 right in here. Okay, then angle DZ, let's change colors here real quick. Okay, angle DZE equals what? Well, that's 20 degrees. Angle MZ or CZD, that's 90 degrees. And then angle A to Z to C, well, upon looking at this, this might seem a little tricky from A to Z to C, but let's do this. This is 180, straight angle, right? I know this is 20, I know this is 90, so 180 minus the 20, we can go minus 90 first if that helps you. That'll give you 90 minus the 20, that'll give you 70. So that's what's left over right here to make this straight angle. So that's 70 degrees. Okay, if ray Z, let me erase some of these things on here. All right, that's better. So let's take a look here. And we are saying if ZB bisects AZ to C, so that means that is our angle bisector right there. Oops, let me get back to the right tool here. Then the measure of angle what equals the measure of angle what? That would mean the measure of angle 2 is equal to the measure of angle 1. And then the measure of angle 1 here on the next problem, we're looking at number 6, plus the measure of angle 2 plus the measure of angle 3. So the measure of angle 1 plus 2 plus 3, here is the perpendicular. These add up to be 90 degrees. So moving on to the last couple problems. The measure of angle 3 equals 20 degrees. The measure of angle 2 equals 3x minus 5. And the measure of angle 1 is 2x plus 10. Find the value of x. So this kind of got put off way over here, but that's what we're finding the value of. So we know angle 3, we know angle 2, we know angle 1, and we know when we add these up, we already said that these come out to be 90. So 20 plus the 3x minus the 5 plus the 2x plus the 10 equals 90. So let's work this out. So 3x and the 2x gives me 5x. Over here, 20 minus the 5 plus the 10, that'll give me plus 25. And then we have equals 90. So 5x equals 90 minus the 25 comes out to be 65. And then x will end up being, divide that by 5, 13. Find the value of x, we did that. Okay, so constructing congruent angles, there is a video on that, and I will talk about that in class, in addition to this one, constructing the angle bisector. These are separate videos that I have for you, and I will talk about them in class as well. All right, so hopefully this lesson helped. Make sure to like and subscribe, and I'll see you guys in the next video.